Welcome back, everyone. Last time we talked about enthalpy and entropy. Today we're going to think about both of those concepts when thinking about the spontaneity of reactions and then also Gibbs free energy. So what is spontaneity or spontaneous? I kind of have a little picture there on the right hand side. I kind of like that quote. It's something you say if you're doing something in life and you do something that's spontaneous, as performed or occurred as a result of a sudden impulse or inclination without premeditation or external stimulus. So you kind of just go for it and do it. All right. So with spontaneous, when you think about spontaneity with reactions, they occur. All right. The opposite, that would be non-spontaneous, where we're going to need some stimulus in order for it to occur. Spontaneous reactions will just occur naturally how they are. So nature loves the spread of both energy and matter. So we talked about the spread of energy with enthalpy and the spread of matter with entropy. For a reaction to be spontaneous, when we think about enthalpy, we talked about those exothermic reactions. So giving off heat, those are going to be spontaneous. So we have that negative change in enthalpy. We'll have that favorable reaction. And then when we think about entropy, when the products have more disorder. So say we go from a liquid to a gas, the products then have more disorder, and the reaction is going to be favorable. All right, and here the reactions, we're going to have a positive change in entropy. So we're going to use both of those ideas of how favorable they are in thinking about the favorability of reactions. And what we're going to talk about is we're going to talk about Gibbs free energy. So that's going to describe how spontaneous a reaction is. And it's the energy of a chemical reaction that can be used to do work. Right. So here on the slide, it says a thermodynamic variable that combines both enthalpy and entropy. So we're going to have an equation that's going to use both enthalpy and entropy. We're also going to think about temperature. So here is the equation. We have Gibbs free energy equals a change in enthalpy minus the change minus the temperature times the change in entropy. So how do we know that a reaction is going to be spontaneous? Is if the change in Gibbs free energy is negative. So we get a negative value from this equation, we know that the reaction is going to be spontaneous. If we get a positive value, the reaction is going to be non-spontaneous. So here down at the bottom of the slide, I have what the symbols here represent in the equation. So delta G equals Gibbs free energy, delta H is the change in enthalpy, delta S is the change in entropy, and T is the temperature. We're going to find out that we're going to want that in Kelvin. All right. So let's look at a Gibbs free energy calculation. This is on page 3 of your guys' chapter packet. So we're going to calculate Gibbs free energy for the following reaction, 25 degrees Celsius, given that the change in enthalpy is 28.05 kilojoules and the change in entropy is 108.7 joules per Kelvin. So there's a few things here to kind of point out is that if we look at our units, when we look at enthalpy, it's in kilojoules. And our unit for entropy is in joules. So we're going to have to get a common unit. So I would recommend going to joules. It's a lot easier to convert to the smaller unit than up to the bigger unit. So I'd recommend changing that enthalpy to joules. And then we also have to look at the entropy units. You have Kelvin there, so remember you got to put your temperature in Kelvin. And I have provided the chemical reaction here for you. So if you guys would take this time and think about how you can use this equation here for Gibbs free energy in order to solve for this, whether this reaction is going to be spontaneous or not spontaneous. So I recommend pausing the video right now and seeing if you guys can solve for that. So here are the numbers you plug in. I converted my enthalpy into joules in order to get that common unit with the entropy. Minus the temperature in Kelvin, so 298 Kelvin, times 108.7 joules per Kelvin. All right, and so that's our entropy. When we carry this out, we'll end up with delta G being a negative roughly 4,300 joules. If we think about the significant figures, 25 degrees has 2 significant figures, so our answer should have 2 significant figures. So we have that negative 4,300 joules. Now we got to think, all right, is this reaction going to be spontaneous or is it going to be not spontaneous? So if we look at the whether the Gibbs free energy change is positive or negative. It's negative here, so that's going to tell us that our reaction is indeed spontaneous. So what would happen to spontaneity if temperature is increased? So if you look here at our equation of Gibbs free energy, if we multiply that entropy by a larger number, so if we would have a higher temperature, we'd multiply the entropy by a higher number, we would get a much larger value there, and we're subtracting it from the change in enthalpy. And so our value is just going to keep getting more negative and negative and negative the higher the temperature that we go here in this case. All right. And so spontaneity would increase with temperature because we would just keep subtracting a much larger number if the temperature were to increase from our initial change in enthalpy. All right, so now let's look at a few examples here. We're going to have 4 of them. And we want to determine if the following reactions are spontaneous or non-spontaneous, and determine if they're enthalpy or entropy driven. And how would an increase in temperature then affect spontaneity? All right, so I'd recommend pausing the video here and seeing if you guys can explore these yourself and come up with an explanation, and then replay it so you can hear my explanation of them. So when we look at A, we have a liquid and a gas reacting, going to a gas and a gas. So if we also look here, the change in enthalpy is provided for us. So it's negative, so that means it's going to be favorable. And then we also think about entropy. Are we going from we're going from liquid to gas and gas. So we're going to a more, all of our products are in a much disordered state. They're all in gases. And we also go from 4 particles on the left-hand side to 5 particles on the right-hand side. So that's also going to tell us that it's favorable with entropy. So this one's going to be both enthalpy and entropy driven. It's going to be spontaneous. All right, an increase in temperature then would also increase the spontaneity. We look at B here. If we look at the change in enthalpy, it is positive. So we know it's not going to be favorable with enthalpy. If we look, we're going from a gas to a liquid and a gas. So we're going to a liquid which is more organized. So with that, entropy wouldn't be as favorable. Also, we're going from 5 particles to 4 particles, which is also not going to be favorable with entropy. And so in this case, neither enthalpy nor entropy driven. It's going to be non-spontaneous. An increase in temperature then decreases the spontaneity. So if we keep increasing temperature, it's just we're going to end up with a value that keeps getting more and more positive, because the entropy here would be negative, and it was just a negative times that negative would just become a positive, and so it would just keep getting a bigger and bigger number for our Gibbs free energy. We look at C. This is going to be enthalpy driven. So if we look, we have a negative value for our change in enthalpy. So that's how we know that it is indeed favored with enthalpy. Now, if we look here, we're going from the xenon and the fluorine particles. They're both in the gaseous state, and we're going to a solid. We're going to a gas to a solid. It's going to be unfavorable because it's going to be more organized as far as entropy. We're also going from 2 particles to 1 particle, which again, it's going to be unfavorable for entropy. And so more information is going to be needed to determine spontaneity, because it is enthalpy driven, but entropy is not necessarily favorable. And so we would have to plug in the values here in order to see if we would get a negative value for delta, or the change in Gibbs free energy. And also here, an increase in temperature is going to decrease spontaneity because it is unfavored with entropy. And so if we have a positive value for entropy, or actually in this case, we would have that negative entropy. And so we would have, if we increase temperature, we're going to have that same case as the last time. We're going to have that negative times a negative, which is going to turn to a positive. So we're going to keep adding it on to the change in enthalpy value there. Once we get to a certain temperature, it's going to make Gibbs free energy positive, which then is going to be unfavorable. All right, so that's why it would decrease spontaneity. If we look at D here, go from a solid to a gas, we know that that is entropy driven. And then we also, with enthalpy, we're not given a change in delta. We're not given a change in enthalpy here. So we know it's entropy driven. We're going to need more information in order to determine the spontaneity because we don't know the change in enthalpy. But we do know an increase in temperature is going to increase spontaneity because with an increase in temperature, if we think of our equation, our delta S, which is our change in entropy, is going to be a positive value here. So we keep multiplying it by a much higher temperature. It's going to make that negative, the value being subtracted from the change in enthalpy, higher and higher. And remember, we want that negative value for a reaction to be favorable. And so if we keep getting a value higher and higher there being subtracted from the change in enthalpy, we'll end up increasing the spontaneity of the reaction. Right. So with these, you really have to think about the Gibbs free energy equation, and then also thinking about enthalpy and entropy, whether the situation is for when it's favorable and then unfavorable. Here I kind of have a summary of everything that we've talked about in a chart to kind of help organize your thoughts. And you can also think about the Gibbs free energy equation here. All right. So if both values, let's look at the third one down there. So say the change in enthalpy is positive, the change in entropy is positive. We're considering the sign of the change of Gibbs free energy. And so it's going to be spontaneous at a very high temperature because we need to get that temperature times the change in entropy, that value to be very large. We need for it to be larger than the change in enthalpy there so that we get that negative delta or that negative change in Gibbs free energy. So a higher temperature would ensure that we would at some point probably get to that point where we have that negative change in Gibbs free energy. For next time, we're going to learn about the collision theory and also reversible reactions. So what spurns a reaction on? How can we increase the reaction probability? And then also reactions being able to go back and forth, so reversible reactions.